This is Biomaterials, Lecture 9, Video 1. In this lecture, we will begin our discussions on biomaterials that are used to replace biological materials. It is my hope that the last 7 lectures have given you some appreciation for the soft and hard tissues that are in your body. If I did my job correctly, you should now have an understanding of the complex relationships between the structure, composition, synthesis, properties, and performance of bone, ligaments, tendons, muscle, cartilage, and elastin. Now, how do we replace these biological materials if something goes wrong? For example, are there biomaterials that have similar performance and properties as bone, which has properties that are dependent on strain rate and can restructure itself to optimize its performance? Not yet. But that's not going to stop humans from solving the problems of our mortal bodies. In this lecture, we will focus on biomaterials that millions of people have, and some of you may already have. We will focus on biomaterials that alleviate problems in teeth or replace the teeth themselves. As we focus on these biomaterials used in the mouth, you will learn about the thermal properties of materials. In this lecture, we will discuss heat capacity, thermal expansion, and thermal stresses. You will learn that as a solid material absorbs heat, its temperature rises and its dimensions increase. I will mention this again because it is important. The concepts that you learn in biomaterials are not just applicable to biomaterials, but to all materials. Thermal properties of materials are important in a broad range of engineering applications. So, let's talk about tooth decay. Here is a perfectly good set of teeth. You should now be familiar with the structure, performance, and properties of dentine and enamel. Teeth are a fascinating example of a composite material made by nature. However, if you don't take care of your teeth, cavities will form. And a really bad case of cavities is shown here. This is a very painful situation to be in. Imagine how this person feels every time they eat or even whenever they close their mouth and put their teeth together. How did this happen? What causes cavities? In summary, cavities are caused by a combination of acid, sugar, bacteria, and time. Bacteria in the mouth consume the sugar that is in the food that you eat. This bacteria excretes acid. Enamel has a high mass fraction of hydroxyapatite, which, as you learned, is a strong ceramic. However, the acid produced by bacteria can dissolve hydroxyapatite. Over a long period of time, such as weeks of not brushing teeth to get rid of that sugar, the acid erodes the hydroxyapatite and eventually hits the dentine. Dentine erodes much faster than enamel because it is composed of hydroxyapatite and collagen, which makes it softer than the enamel. Eventually, this erosion hits the pulp of the tooth, which contains very sensitive nerves and blood vessels. This stage is very painful. So, how do we fix this common problem of cavities? With biomaterials, let's take a look at dental fillings. Dentists solve the problem of tooth decay by first removing it completely through drilling and then filling in the void with a biomaterial. The 3 biomaterials that are widely used as dental fillings are gold, composite, and amalgam. Let's first focus on gold. Here you can see the process of installing a gold filling. First, the cavity has to be removed. Second, the dentist shapes a piece of gold that fits the specific shape of the void that was created. This is called an inlay or onlay. This piece of sculptured gold is then installed into the void. A dentist who installs gold fillings is not just a dentist, but is actually also a sculptor. Here is a video of how gold fillings are installed on teeth.
When the biting surface of a back tooth needs a restoration, an excellent choice is often a gold inlay or onlay. Which one we recommend depends on how much of your tooth structure has been lost. An inlay fits within the grooves of a tooth's biting surface like a filling, while an onlay also covers one or more cusps of the tooth. Both kinds of restorations are precision crafted in a dental laboratory, so it may take 2 or more appointments to restore your tooth with a gold inlay or onlay. On your first visit, we numb the area to make you comfortable. We may also use a rubber dam to protect your mouth while we work. Then, we remove any decay and shape the tooth with the handpiece. Next, we'll take an impression of your teeth. The lab uses the impression to make a model of your mouth. They'll use the model to create a final restoration that precisely fits your tooth and bite. In the meantime, we often place a temporary restoration. On your next visit, we remove the temporary and try in your final gold inlay or onlay. We check the fit and your bite. When everything looks good, we cement the final restoration in place.
Sculpting gold fillings is both time-consuming and expensive. Another solution to fixing cavities is to pack amalgam into the void that is formed when a cavity is removed. Amalgam is an alloy in which one of the component metals is mercury. Mercury is needed because it is liquid at room temperature. Mercury can react with other metals such as silver or tin to form a plastic mass. This plastic mass can be packed into a cavity. After mercury is mixed with certain metals, a reaction between the metals happens, which hardens the plastic mass over time. An example reaction is shown here. The typical composition is anywhere between 45 to 55 weight percent mercury, anywhere between 35 and 45 weight percent silver, and around 15% tin. Here is a video of how amalgam is prepared and installed in teeth.
To begin with, I will take half a scoop of dental amalgam alloy. See, this is half a scoop. Then this is mercury, liquid mercury. I would carefully dispense 1 drop of mercury in it. Take the pestle, hold it in this way. It applies a lot of pressure. Keep it here and go on mixing. Slowly I would press the alloy to the walls of the mortar. You have to keep until you get a shiny appearance.
A dental composite is another biomaterial that is used to address the problems associated with cavities. As the name implies, a dental composite is indeed a composite. This slide shows the process of installing a dental composite in teeth. Dental composites consist of a polymer matrix, which are typically the ones shown here. Ceramics are typically used as the dispersed phase in these composites. Hard ceramics such as silicon dioxide or zirconium dioxide are used as fillers. Nanoparticles are even used in these applications. The important thing to note here is that a composite is needed in this application. The polymers shown here do not have a hardness that matches enamel. Harder ceramics are needed in teeth. However, it is very difficult to shape a ceramic to match the specific shapes of the voids in teeth. And pouring ceramic powder into the voids will not keep the ceramic powder there. The polymer matrix is needed to keep the ceramic particles together and also conform to the shape of the void. The ceramic filler is needed to achieve the hardness necessary for eating food. Remember the key idea of composites that you learned in Engineering 86. Composites are artificially produced, multi-phase materials with desirable combinations of the best properties of the constituent phases. The polymer matrix and ceramic filler in dental composites achieve desirable combinations of the constituent phases. If you'd like to review composites, a link to the relevant Engineering 86 lecture is provided below. After packing the cavity with polymer and ceramic, a curing step is needed. A photoinitiator that is mixed in with the filling enables the polymer to cross-link and harden. Without the photoinitiator, the polymer will remain soft, which is not a good state to be in when used in teeth. The following video will show you how dental composites are installed in teeth. However, I must warn you that there will be drilling of teeth shown. If this is something that you don't want to see, please feel free to skip ahead by about 3 minutes. So there you have it. The biomaterials that are commonly used to replace the enamel in teeth have sufficient mechanical properties to do the job of enamel, but they are less hard and may need to be replaced every few years. But what about other properties? We focused on mechanical properties. What about other relevant properties? Well, this slide shows the thermal properties of enamel and dentine, which are highlighted in blue. Note that gold, a replacement for enamel, has higher thermal conductivity and higher linear thermal expansion coefficient than enamel and dentine. So what is thermal conductivity? What is thermal expansion? What is specific heat? Let's dive into these thermal properties. Please watch the following video, which is an X-ray of a person drinking a beverage. As you watch the video, think about the possible range of temperatures that your teeth can encounter when drinking hot and cold beverages.
Recording.
Good, video off.
Recording.
Okay, video off.
Recording.
No.
So, what is the temperature range of the mouth? You very likely have taken a sip of an iced beverage at some point in your life. How cold was that beverage? How cold can an iced beverage get? There is an answer to that, and you may read about it in the article that is linked in the description below. Reading the article is not required. It is merely there in case you're interested. According to this article, it is not a good idea to drink anything colder than -4 degrees Fahrenheit or -20 degrees Celsius. That's the lower limit for safely drinking a cold beverage. But what about the upper limit for beverage temperature? Many of you watching this video may have enjoyed a hot beverage at some point in time in your life. What's a safe upper temperature limit for beverages? There's actually a scientific publication on that. It is also linked in the description below if you're interested in reading it. Again, it's not required. But based on this paper, hot chocolate and coffee can be served at temperatures as high as 185 degrees Fahrenheit or 85 degrees Celsius. So your mouth can actually encounter a wide range of temperatures depending on what you eat and drink on a given day. Let's focus on what happens to a material when it is heated up. As a solid material absorbs heat, its temperature rises and its dimensions increase. As you learned in Engineering 86, if you heat a material to a high enough temperature, a liquid phase will form, or it will become completely liquid. Thermal properties that are critical in the practical use of materials are heat capacity, thermal expansion, or lowercase alpha, and thermal conductivity, or lowercase k. Each of these properties are influenced by atomic motion around equilibrium lattice positions. Let's first turn our focus to heat capacity. The heat capacity of a material is a measure of how much heat energy must be added to increase the temperature of a mole or a kilogram of a material by 1 degree Celsius. Heat is given by capital Q, and temperature is given by capital T. Typically, heat capacity is specified as per mole or per kilogram of material. Because it is relatively easy to do, the heat capacity of a material is usually measured at constant pressure. This is given by C sub P, which is equal to the derivative of Q with respect to the temperature at constant pressure P. Heat capacity can also be measured at constant volume. This is given by C sub V, which is equal to the derivative of Q with respect to temperature at constant volume V. Please know the difference between C sub P and C sub V. Let's apply what we've learned. Here you see Kermit the Frog drinking a hot cup of tea. Let's assume that Kermit just drank a cup of ice cold water and immediately starts sipping hot tea. Don't ask why, just assume this wacky scenario is actually happening. After all, we are looking at a frog drinking a hot cup of tea. Let's also assume that one of Kermit's teeth has a gold filling in it with a mass of 5 grams. What is the energy required to raise the temperature of the filling from 0 degrees Celsius to 85 degrees Celsius if the specific heat of gold is shown here? Note that the specific heat at constant pressure is given by little c sub p, which is equal to the heat capacity at constant pressure divided by mass. The equation for calculating this energy is not given here, but a hint on how to perform this calculation can be seen in the units of specific heat. Note that energy is in joules, and you are given a mass and temperatures in the problem statement. Your options are shown here. Please click on the link below to complete this in-lecture question and receive credit for your work. This is an open book, open note assignment. You may take as much time as you need, but the important things to remember in these in-lecture assignments are that you do not ever hit the back button on the form and you complete the questions before starting Lecture 9, Video 2. We trust you to follow the honor code. We will go over the solutions to this problem in Lecture 9, Video 2, which is also linked below.